Today we are going to continue our discussion on thermodynamics that we have started from the last class. So, in the last class, we have actually tried to understand what are the basic terminologies of thermodynamics are. We went through typical definitions of universe, system, and surroundings, and how the open systems or the closed system or the isolated systems, such kind of definitions are defined. Now, in our today's class, before going deep down into the basics of thermodynamics, we will try to understand like what are the states of the system. In the last part of the last class, I gave you a glimpse about the idea about the states of the system. Now, as you can see in thermodynamics, a different and a much simpler concept of the state of a system is introduced. Now, in thermodynamics, in the last class, I have told you that it is all about dealing the microscopic, not the microscopic systems, but the macroscopic ones. Here you can see, here also I have mentioned that it actually gains the detailed knowledge of motion of each particle because we deal with average measurable properties of the system. So if we have some n number of molecules, suppose we have capital N number of molecules in a system, and in another system we have small n number of molecules. One is acting as the macroscopic version, and the another one is acting as the microscopic version. In thermodynamics, we do not need to know about motion of each and individual particle. So as a whole or as a sum, we have to gain the knowledge of the measurable properties of the system, and then we take an average. For example, if you can take up, suppose we have 10 molecules which are designated as N1, N2, dot dot up to N10. Suppose this N1 molecule has a velocity, a particle velocity of V1, this N2 having a particle velocity of V2, and the N10 one having a particle velocity of V10. So any nth particle is having a particle velocity of Vi, where I is equal to 1 to 10. So if we have this ensemble or system where any nth particle is having a velocity of Vi, then we do not need to know about the each and individual velocity of the particle. So we do not need to know N2 is having how much velocity or V2. We do not need to know the velocity of V3 or V10 or any Vi. But what do we need to know? In thermodynamics, we are only concerned about the average measurable property, that is the V average. So we are concerned about calculating the average measurable property V average of the system. So I guess you guys are having an idea what we are trying to do. In thermodynamics, such kind of measurable properties are termed as the state functions or state variables. So this is very important in the field of thermodynamics when we are discussing about the first law. In the last class, I have told you about the zeroth law of thermodynamics, but I have not mentioned that in the class because of you guys to understand. Because we have in thermodynamics some zeroth law, first law, second law, and the third law. In the first class, I have given you a glimpse about the zeroth law. But in this class, we have started talking about the first law of the thermodynamics. And to gain an idea about the first law of thermodynamics, we need to know and we need to specify the state of the system by state functions or state variables. Now, there are several state variables. As you can see, they are characterized over here: pressure, volume, temperature, number of moles, etc. pressure is represented by P, volume by V, temperature by capital T, number of moles by small n. So these are classical representations of our state of functions or state variables. Apart from these, there are other state variables also, just like internal energy, enthalpy, etc. So gradually we will know what are these things. So when we talk about our chemical system, which is either losing an energy or gaining some energy, we need to introduce a quantity which represents the total energy of the system. The total energy of the system, the energy can be chemical, it can be electrical, it can be mechanical. As you can see over here, the energy that is gained or released by the system either can be chemical or electrical, it can be mechanical, or it can be any other type of energy that we can think about. So the sum of all these energies of the system, be it chemical or electrical or mechanical, they togetherly they are called as the internal energy U of the system. Now the internal energy U of the system may change. It does not remain constant throughout the course of a thermodynamic parameter. So there you can see the heat passes into or out of the system. In that case, the internal energy gets changed. If some amount of work is done on or by the system, and lastly, if the amount that is contained by the system, so the matter that is actually inside the system, either it enters or leaves the system. So if I give an overview over here, so here we have suppose N1 to N10 particles which have different kinds of velocities, V1 to V10, N1 having a velocity of V1, N2 having a velocity of V2, and any nth particle is having a velocity of Vi, where I is equal to 1 to any possible integral number. So we do not need to know about the individual velocities. On an average, we need to know the average measurable property of the specific state. So here I have given you a glimpse about the internal energy concept. The internal energies concept was actually introduced because in thermodynamics we needed a linker between the work function. The linker was actually very much required in thermodynamics. If we are actually uh, trying to understand the states of the system, the state variables, the internal energy plays a crucial role. So if you are considering a system which is trying to lose some energy or which is trying to gain some energy, then this specific parameter of internal energy comes into picture. Look, inside a specific system, there are some crores and billions and trillions of molecules. Each of these molecule can have some chemical energy, they can have some electrical energy, mechanical energy, or energy in terms of any kinds of form, and the sum of the total energy content of the molecule is called the internal energy. Here I will give you a very good idea about how we can calculate the internal energy. Remember, internal energy cannot be calculated by us in physiological manner. The change in internal energy can be calculated. So if I actually show you like what is pressure or volume or temperature of a system, you can calculate all these two, all these things. But when it is internal energy U of the system consists of all the kinds of energy of all the particles present inside the system. This U cannot be calculated, which is the internal energy of the system. It changes as I have shown you under various circumstances. Either heat passes into or out of the system, either work is done on or by the system, or if the matter is entering or leaving from the system. Under this scenario, internal energy of a system can change. So I guess you are having a clear cut idea about the internal energy and also the change in internal energy. The change in internal energy can, however, be calculated very smoothly. So here actually it is coming as a very interesting factor to you, because the property itself, the property cannot be measured by physical quantitative manner, but the change in the property can be actually calculated quite easily. So the internal energy is a state function. In thermodynamics, it is designated as U, and is U cannot be calculated, but however we can very easily calculate del U, which is change in the internal energy. Now, after we have discussed a lot about the typical parameters present in this thermodynamical point of view, we will first deal with the zeroth law of thermodynamics that we have started in the last class. The zeroth law of thermodynamics, as you can see over here, which deals with the temperature of the system. And while it may seem intuitive to us that the terms like what do you mean by temperature or what do you mean by system, it is very important to define these terms. And in the last class, I have given you a brief idea about the system surroundings and the universe kind of point of views. In universe, it is directed by everything. System is subset of the universe that is being studied or that is under the measurement. As surroundings is the every part of the universe that is not the system itself. So system and surroundings as a whole form the universe. And after that, I have also given you that the depending upon the nature of the wall or boundary that is separating the system from the surroundings, specifically whether it allows the transmittance of matter or energy across it. So between system and surroundings, there is always some kind of interaction by means of matter or energy. Depending upon the nature of the boundary or the wall that is separating these two, we can define some different systems. In the last class, I have already told you. So this is a brief overview and the key points: the open system, the closed system, and the isolated system. Open system allows for both mass and energy transfer across the boundary. In a closed system, it allows only for the energy transfer across the boundary, but not any kind of mass or matter transfer. And the isolated system allows neither mass nor energy transfer across the boundary. So this was classification or segregation of systems depending upon the nature of the boundary. Further, systems can be differently characterized. First one is the homogeneous. In homogeneous system, they consist of only single phase of matter and with uniform concentration of all the analytes or substance present throughout the system. Suppose you have a glass of water and I put some handful amount of calcium chloride inside this glass of water. Take it quite well and keep it standing for some minutes. This actually forms a calcium chloride in water forms in homogeneous solution. In a homogeneous solution, the matter of the phase of the matter remains single. So it will be throughout same. So in some cases you can see in the system there are some parts of solids, some parts of liquids. Those are not called homogeneous system. In homogeneous system, the analyte or the substance is the phase remains constant or single throughout every course of the system. If it is solid, it is solid everywhere. If it is gaseous, it is gaseous everywhere. But the example of mud is not the same. You see, in muddy systems or in clay system, some part is liquid and some parts are solid. So these are not homogeneous systems. These are termed as heterogeneous systems. Mud is a very classical example of an heterogeneous system, which contains multiple phases and or varying the concentrations of the constituents or the substances throughout. Now, it is a very important variable actually is there that describes the system as its composition, which can be specified by number of moles or small n. The small n is the number of moles of each component, of the concentration of each component. The number of moles of a substance is given by the ratio of the number of particles to Avogadro number. Suppose we have some 10 to the power 100 number of molecules in a specific system. We have a system. Let us take this calcium chloride in water system for easy understanding. Let us say this calcium chloride in water system consists of 10 to the power 100 number of molecules. And these 10 to the power 100 numbers of molecules are there. And if we divide this number with the help by Avogadro number, which is defined as Na, that is 6.023 into 10 to the power 23 per mole. This is the Avogadro number, and capital N is the number of particles, be it atoms, be it molecules, or be it formula units. So the number of moles N will be defined by capital N divided by capital Na. So total number of molecules of the particle divided by the Avogadro number of the molecules gives us the number of mole. You see, this capital N is simply a number which does not have any unit, and this Na, which is in the denominator, has a unit of mole inverse. So as we can calculate the N, which is number of moles, this is inside the denominator, the mole inverse goes to the numerator and becomes mole. That's why N is having unit of mole. So this actually proves our definition that N by Na mole inverse is leading to mole. So mole is the number of moles of the substance. So here we have talked about some different universe, system, surroundings definition, open system, closed system, and isolated systems definition that I have already given you an idea in the last class. And next, depending upon the homogeneity or heterogeneity of the system, there are two different kind of system that I have introduced you homogeneous and the heterogeneous system. In homogeneous, there consists only a single phase of matter and an uniform concentration of all the substances present. We have heterogeneous system which consists of multiple phases and or varying concentration of the constituents. And also we have introduced a very important parameter or variable which is N, that is number of moles of the substance. Number of it is defined as capital N, which is total number of molecules present divided by capital Na, which is Avogadro's number. So now we have all now come up to the other important variables, which I have just told you in the last slide about the state variables or the state functions. Here you can see we can describe a system by variables of pressure, temperature, volume, and other variables can also be important, which are known as popularly state variables. Now, knowing a small number of state variables is all that is required to determine all the other properties of a system. So, there is a system which consists of some of the state variables. We need to know minimum number of the state variables parameter. Then only we will be able to assign the other state variables, and that actually will help us in determining all the other properties of a system. The relationship that is allowing us for the determination of properties from the values of a couple of state variables is a call of the equation of state. So here comes the equation of state, which I introduced you in the last class in the last section. So here you need to know what is the equation of state. It is a relationship that is allowing us to determine the properties of a values of a couple of state variables. So basically we need to know the value of couple of state variables, and then only we can determine the other properties of a system. Here comes the properties. We can be It can be designated as intensive or extensive properties. Now let us come to this paragraph which tells us about the intensive and the extensive property. So now currently I am focusing on this paragraph which actually tells us about the intensive or the extensive property of a system. Now variables that can describe a system can either be intensive or be extensive. Now generally you may ask, or this question may arises inside your brain, that what are these properties and how will I say or assign that this function or variable is intensive and this is extensive. So let me help you in this regard. The intensive properties are those which are independent of the amount of any given substance present in the system. And extensive properties are those which are dependent on the amount of substance that is present. Let me try to make you understand by means of a very good example. You see, suppose we have a container, and in this container we have 10 ml water. We have another container which has 3 ml water. So in a container we have 3 ml of water. In another container we have 10 ml of water. Both of these containers are heated at 50 degrees Celsius. So both of these containers are put in the Bunsen burner or any kind of oven you can take up as a choice and heated at 50 degrees Celsius. So after 10 minutes or specific amount of time, you will see this container A and container B has same temperature, which is 50 degrees Celsius if you measure by a thermometer. So after some t equal to 10 minutes, let's dip a thermometer inside this bowl and also a thermometer inside this bowl. Both the thermometers will show that the temperature of the systems are 50 degrees Celsius, though this water has a volume of 3 ml and this container has a water of volume 10 ml. So you see the temperature, be it 3 ml of water or be it 10 ml of water, whatever amount is present in the container is not affecting the temperature. So temperature is an intensive property of the system. Because in the definition I have told you, the intensive properties are those which are independent of the amount of any given substance present in the system. Because 3 ml have some different moles of molecule, moles of water, and 10 ml of water has different moles of water. Because the volumes are different, the amounts are different, and since the amounts are different, the number of moles of the two systems are different. Though the number of moles are different, still the temperature of these containers are same, that is 50 degrees Celsius. So the temperature does not depend on the amount of substance that is present in the system. Here, that's why we call temperature or color are the examples of intensive variables, whereas volume and mass are examples of extensive variables. You can clearly understand why volume and mass are examples of extensive variables. The value of the intensive properties is that they can be conveniently tabulated or calculated for various substances. But for extensive properties would be specific to individual systems. Now here comes general trivia that I'll share with you. The ratio of two extensive variables can be and intensive variable. So this is a very interesting phenomena that I am going to discuss. Suppose we have one extensive variable EV, one, and we have another extensive variable which is EV2. We have EV1 and EV2, and both are extensive variables. Now, if we take up a ratio between these two, which results in another variable V3. Now, V3 can be an intensive variable, which is very interesting. Let me also discuss this phenomena with with an example. Let us take the ratio between mass and volume. You see, mass is designated as M and volume is designated V. Now, you know that mass is an extensive variable because it is dependent upon the amount of substance. If the amount of substance is more, the mass will be obviously more. And also, we have a volume parameter. The volume, you also know, if the mass, the amount of analyte or substance present inside a system is more, the volume will also be more. So both of mass and volume are extensive variables. But if we take up a ratio between these two, the ratio between mass and volume, we all know what is the ratio between mass and volume called. It is called density. Density is actually determined or designated by D or rho, this parameter. So M by V is density, but density, if you can see, is actually an intensive property because the amount of substance that was controlling between the intensive variable and the extensive variable has actually got cancelled out. So density, being the ratio of two extensive variables, is itself an intensive variable. So I'll give you another example, that is molar volume. Molar volume is nothing but volume per mole of the substance. You see, volume is an extensive property because it depends on the number of molecules. But if we, because you see here, if you have a volume, suppose you have volume of 10 or 100 ml, let us say, we have 100 ml of volume and we are having number of moles 10. So here we are having V is equal to 100 ml and N is equal to 10. In this case, suppose we have volume of 1000 ml and we have number of moles as 100. So we have two sets. In one set we have volume of 100 ml and we have number of moles of substance presence is 10. In another case, we have 1000 ml of volume and we have number of moles as 100. You see, when number of moles of N got increased from 10 to 100, the number of the volume got increased from 100 to 1000. So here we can see that if the number of moles is increasing, the volume is also increasing. That's why volume is called an extensive property. But if we can come up with the concept of molar volume, that is Vm. In this case, what is Vm? Vm is 100 divided by 10, which is 10 ml per mole. In this case, in the second case, if you can see what is the molar volume, this is also 1000 by 100. So this is also 10. So since we are cancelling out the number of molecules present over here, So the extensive variables are dropping to the intensive ones. Here you can see, because 100 is divided by 10, which results in 10 ml per molar volume. And in the next case, if we divide 1000 by 100, we are also ending up on 10, which is the molar volume. So the molar volume of both the systems are same, though the volumes are actually different. So that's why molar volume, which is the ratio of volume and number of moles of a substance, is actually remaining the same, and that's why it's an intensive property which does not depend on the number of amount or solute present in a specific system. For a given substance, you have to know that density is termed as m by v. It is d. Let me actually draw it clearly. We have density, which is mass of the substance present divided by volume, and we have molar volume Vm, which is volume of the substance present divided by number of moles. So if we multiply density, that is D, and molar volume, that is Vm, we end up with this V, and this V gets cancelled out, and we end up in m by n. So m is the mass of the system present, and n is the number of moles of the system present. So here an interesting thing comes out. If you give it an idea, you see, for a specific system, the mass of the system is constant and the number of moles of the system is also constant. So how will you calculate the number of moles? The number of moles is actually calculated by N by Na. N is the number of molecules present in the substance. So if you are dealing with the mass, how we will calculate the mass of the system, or how we will calculate the number of moles of the system? Both of these parameters are constant. Suppose we are dealing with a substance which is having a molecular weight of capital Ma. This is the substance which is having a molecular weight of capital Ma. So how we will calculate the number of moles or the mass of the system? That is something different. The mass of the systems is always constant, but we can actually determine the number of moles of the system. Number of moles here you can see can be calculated by dividing the number of molecules by Na. So N by Na is one of the ways to determine the number of moles, that is N. We have other ways too. Suppose we have a molecular weight of the complex is M, of the system is Ma, which is termed as gram per mole. We have this M is the mass of the system divided by the volume. M was defined as the mass of the system. Here we are actually trying to deal with a molecule which is having a substance of having Ma gram per mole. Ma gram per mole is that amount of substance that is present in gram per mole of the substance. So if we divide the molecular weight of the substance divided by the amount of substance present, that is Ma, what will be the case? So if you give it a clear kind of shot, like what we are actually trying to deal with. We are trying to actually calculate and the relationship between the molar volume and the density. Density is termed as m by v. The m stands for the amount of substance present in the molecule. Suppose we have 10 grams of mass and we have the volume of 10 ml of water. So we will end up in a 1 gram per ml density. 1 gram per ml density will be having. So it is D. And also we have the parameter of molar volume, which is V by N, where N is the number of molecules present. Now, what is we are having the number of molecule present? Now, if we multiply D into molar volume, that is Vm, or it is also termed as V bar, we'll end up this V and this V in the numerator, and the V denominator gets cancelled out. We end up having M by N. N is the number of molecules present in the system. How will we calculate the number of molecules present? That we are trying to think, because we know M is equal to 10 gram. M is a constant and N is a constant. So if M and N are constant, then their ratio M by N is also a constant. So that actually leads to us that the product of D and Vm is a constant, which is K. So D and Vm product are constant. In the case of mathematics chapter, you have actually seen that if we have two parameters or variables x and y, and if their ratio is constant, then they are directly proportional. And if their multiplication or their product is a constant, then they are inversely proportional. So that's why this corollary comes that the molar volume Vm is inversely proportional to the density of the substance. So D varies as 1 by V molar. So this is the corollary we have reached, that the molar volume and the density are inversely proportional to one another. So if we can calculate the number of moles, then it will be much easier. Suppose we have this molecule has a molecular weight of mw in W gram per mole. So how will we calculate the N? N is equal to the number of mass, the amount of mass that is present. So small n is equal to mass of the compound that is present in gram divided by the molecular weight in gram per mole. So here these two gets cancelled out, this gram per gram, and we end up in equal to n is equal to m by mw, which is the molecular weight. And if we can put this, so you see n is equal to m by mw. So if we drag n over the denominator and put mw in the left hand side, we end up in having m by n is nothing but a constant, that is k, and this k is nothing but molecular weight, which is mw. So the product of density and molar volume of a specific substance is always a constant, which is the molecular weight of the substance present. That's why molar volume is inversely proportional to the density of the substance. So I guess I have given you a very good and clear idea about the concept of intensive and extensive variables, how we can define the intensive and extensive variables, how and what factors actually separates these two. Here we have given examples of intensive properties like temperature, color, density, molar volume, etc. And we have extensive properties like mass, volume, etc. Also, we have got an idea that the ratio between two extensive variables can lead to an intensive variable. Just like in case of density, mass and volume are both extensive variables, but their ratio is an intensive variable, that is density. Also, volume and number of moles is an extensive variable property, but their ratio, molar volume, is an intensive variable. And this mathematical situation will be very much useful for you because it is very important for you to understand for the question that I have developed over here, that the molar volume is inversely proportional to the density and vice versa. And what is the product between these two? What is the constant? The constant is nothing but molecular weight of the substance. Now we will come up in the old section of our work and the heat part. So now in the last class I have given you a very brief idea about an equation that I will write up here for your convenience, which is delta U is equal to Q plus W, where delta U is equal to change in the internal energy, Q is the amount of heat that is transferred by the system or transferred to the system, and W is the work done on or by the system. So now we first will change the internal energy. Suppose we have a system like this, which is closed, which has some amount of mass or matter inside with some energy too, which is defined by an adiabatic wall. You can take up the adiabatic wall as a real life example for thermoflask or an insulated beaker. This would not allow the exchange of heat. This would not allow the exchange of heat between the surroundings and the system to the boundary. That's why the term is Q is equal to 0. The Q actually vanishes from the equation and we end up having delta U is equal to W in this case, because it is an adiabatic process. This wall is adiabatic, which does not allow the amount of energy or heat transfer between the system and the surroundings. So in adiabatic process, there will be occurring no transfer of heat between the system and the surroundings, and the wall, this is the wall that is separating the surroundings of the system, is called an adiabatic wall, which is termed as an adiabatic wall. And let us, for example, you can take up this as thermoflask or an insulated beaker. So in this adiabatic wall kind of system where the process is completely adiabatic, so now we will bring the change in the internal energy of the system. So we will introduce delta U in the internal energy system by doing some work upon it. So let us take The initial state of the system which was there was state A, and this temperature that it attained was Ta. So the first state was A, and the Ta was the first temperature. Now the internal energy at the initial state of the system, be it UA, because U is actually used to determine the internal energy. Now we can change the state of the system by two different ways. First one, first we do some mechanical work. Let's say 1 kilojoule by rotating a set of small paddles. Suppose we are actually trying to do some paddling. So by doing paddling, paddling, we are doing some mechanical work which is 1 joule, and thereby we churned the water. And let the new state be called as the B state after churning and doing some paddling. So let's say its temperature be TB, and it is found that upon doing some work, the temperature was got as TB, and TB was much more than TA. TB was more than TA. That means some amount of heat is actually released, or thermal energy is released from the system. So delta T, that is change in the temperature, will be TB minus TA. And since TB is greater than TA, so delta T is equal to TB minus TA, that is greater than 0. Now let the internal energy after the temperature is increased will be UB. So the change in the internal energy will be delta U, which is UB minus UA. So the change in the temperature will be TB minus TA, that is delta T, and the change in the internal energy delta U will be UB minus UA. Now there is another way by which we can calculate, like we can do some work. We do an equal amount of work, which is 1 kilojoule, which is electrical work, with the help of an immersion rod. An immersion rod is something which can actually change the temperature of the system. So we do an equal amount of work, that is the 1 kilojoule of work, which is an electrical work, with the help of an immersion rod, and we will note down the change in temperature too. We found that the change in temperature is same in the earlier case, which is TB minus TA. So be it rotating some paddle and mechanical work, or be it some amount of electrical work with the help of an immersion rod, the change in temperature was same, which is TB minus TA. Now this experiment is actually was performed by a great scientist, which name is J.P. Joule. The kilojoule that you are seeing over here, 1 kilojoule, this J stands for his name only, Joule. So J.P. Joule, between the mid 90s era, he was able to show that a given amount of work that is done on the system, be it mechanical, be it electrical, be it thermochemical. So irrespective of the path, the produces the same change of state as measured by the change in the temperature of the system. So the temperature of the system, the difference in the temperature was actually constant. Depending, it does not depend the path that is taking up. Here you can see the path that is taking is mechanical path. Here you can see the path that is the system taking is an electrical path. Also you can take up a chemical path. So whatever the path is, the change in the temperature of the system will be same. That's why it is called a state function. So it seems very appropriate to define a quantity which is an internal energy U, whose value will be the characteristic of the state of a system. Now the adiabatic work, which is WAD here, the Q is equal to 0. That's why it is an adiabatic work. WAD, which is required to bring that about a change of the system, is equal to the difference of the U of the system, the value of U in one state and that in another state. So delta U will be U2 minus U1, which is WAD. So I will write it again over here for your convenience. Delta U is the change in the internal energy of the system, which is termed as WAD. Why it is converging to WAD? Because it is an adiabatic process I have already mentioned. And in this adiabatic process, we can see that Q is equal to 0. So if the Q is falling to 0, we are left with delta U is equal to WAD. So WAD is the adiabatic work of the system. Therefore, the internal energy U of the system will be such that a state function. The internal energy is U. So U is also a state function. Already we have seen the temperature is a state function. Pressure of the system is a state function. Also U, that is the internal energy of the system, is also a state function because it does not depend upon the path. It is irrespective of the path, but still the change is actually constant. Now the positive sign expresses that WAD is positive when work is done on the system. Similarly, if the work is done by the system, WAD will be negative. So WAD, which is here, it will be positive when work is done on the system. W is done on the system, then the sign of WAD will be positive. It will be greater than 0. But when W work is done by the system, when work is done by the system, we will take up WAD will be negative. So you have to remember the positive sign expresses that WAD is a positive when work is done on the system, and similarly, if work is done by the system, WAD will be negative. So by the system will be negative and on the system will be positive. We will remember by this shortcut trick that on the system greater than 0, by the system less than 0. So on is greater than 0 and by is negative, that is less than 0. So here actually I have tried to tell you some of the familiar state functions. Some of the very familiar state functions are V, P and T. Suppose we bring a change in temperature of the system as from 10 degrees Celsius to 60 degrees Celsius. So 10 to 60 degree Celsius, we have to bring a change in temperature of the system. Now the change in temperature between this initial and final one is 50 degree. Now whether we go straight up to 60 degrees Celsius from 10 to 60, or if we go from 10 to firstly if we go to minus 5 and then we go to 40 and then if we go to 60, then if we take up a different route where we are stopping by two different points, firstly cooling the system to minus 5 then again heating it up to 40, and then again heating it up finally to plus 60 degrees Celsius. We are seeing that the temperature change is independent of the path. There also we are reaching at 60 degrees Celsius. So T is a state function, and it does not value depend on the route that is taking up. So it is independent of the route taken. Also, the volume V of a system. Suppose we are talking about a lake with a specific amount of volume of water in that. It is state function because the change in volume of its water is independent also by the route. Suppose we are putting some amount of water inside this lake by a mug, but the same amount of change when it is observed we are putting by mug by some 1 liter of water. And if the same 1 liter of water is actually done by the system by a tube well or by some other means, that is rain or flood, then also the change of the volume remains also the same, because be it a tube well, be it rain, or be it a mug, they are always the change remains constant. The 1 liter of water will only be added to the system. So here on the basis of work, I have given you very brief idea about the state function, the intensive and extensive variables, and some of the conceptual outcomes. And in the next part of our chapter, we may start with the different kind of heat transfers, and also we will deal with the first law of thermodynamics, where I'll be dealing with some specific problems which will be helpful for you.